Hello students, welcome to System Software Module 1. So in this Module 1, we have two things to remember. One is object code generation for SIC machine, and the other important concept is object code generation for SIC machine. So in this video, we will see how to generate object code for SIC machine. So just before going for the object code generation, we will have to just remember few of the different addressing modes, their values, and we need to remember them for generating the object code. So let's see what are the different addressing modes. And since it is SIC machine, we have to know that I hope all of you remember that we have four different formats we have for data representation. So the first one is format 1, takes 1 byte of memory, that is 8 bits of memory. So that means it occupies the opcode will be taken for in format 1 representation. So in format 1 we have 8 bits, and all the 8 bits will be occupied by the opcode. And then in format 2 we have 2 bytes of memory, that is 16 bits of memory, and these 2 bytes of memory will be reserved for two registers. So no, again there is no memory as such given in format 2. Now in format 3 and format 4, they have memory also in them, so that the values can be loaded or accumulated, or can be moved from one memory location to another. So format 3 takes 3 bytes of memory, that means 24 bits of memory location. So out of this format 3 bytes, the first 6 bits, okay, 6 bits will be taken by opcode, and the next bytes, that is the next NI, BP, XE. So these 6 take 1 byte each. Okay? And then the next 12 bits will be reserved for the displacement. I hope you remember that. Okay, and in format 4 we have 4 bytes of memory, that is the first 6 bits will be for opcode, and the next 6 bits will be for NI, BP, XE, and the next 20 bits are reserved for displacement. Okay, so this was just a recap of all the different formats of SIC. Now we will come back to the addressing modes. So let us see what are the values for addressing modes. So we know that we have BP, NI, XE, and each one will be taking the value either 1 or 0. It is like true or false. Okay, so let's see each one in detail. Okay, so the first one, when E is 0, E stands for exponential representation. So when E is 0, that means it is a format 3 of SIC. It represents format 3 presentation. Then E is equal to 1 means it is format 4 representation. So this is very, very important. So whenever it is a format 4, then we have to make E as 1. If it is format 3, it is E is equal to 0. And then we will come to the combination of B and P. B stands for base addressing, then P stands for program counter relative addressing. Okay, so B is equal to 0, P is equal to 1. So 0, I mean, like everybody will just relate it with 0 or 1 value, that is false or true value respectively. So what do you mean by 0? That means base relative addressing mode is not there. Okay, so B is 0, P is equal to 1 means it is PC relative addressing mode. That means it is program counter relative addressing mode. So what is program counter means? It will know the next address. It will be knowing the next address. So we call it as PC relative addressing mode. So for this, how do we find the displacement is target address plus program counter address. So this we should be knowing, and usually this will be the default mode. Usually we will go with this. Then we have B is equal to 1 and P is equal to 0. So what do you mean by B is equal to 1? That means it is a base relative addressing mode, because B has become 1. It is true kind. So base relative addressing mode, and program counter will be 0. So we call it as base relative addressing mode. And how do we calculate this displacement? Is nothing but target address plus the address of this base. Okay, address of base will be given. And the next combination is both b is equal to 0 and p is equal to 1. So when both b is equal to 0, p is equal to 0, then we call it as direct addressing mode. So here displacement will be just the target address, because we don't have any base address, we don't have any program counter address. So displacement will be just t. And we are supposed to have one more combination of b is equal to 1, p is equal to 1. But that is invalid. We cannot have both as 1. Okay, so the next combination, we just have one x here. So x is equal to 1 means it is indexed addressing mode. Okay, that means whenever we get the instruction, the registers will be included in the instruction. So that kind of instruction we call it as indexed addressing mode. Then we have another combination n and I. That is n is for indirect addressing mode, then I is for immediate addressing mode. So indirect, then immediate. Okay, so let's see the combination. When n is 0, I is equal to 1, I told you what is I. I stands for immediate addressing mode. So n is 0, I is 1 means immediate addressing mode is activated. So it is immediate addressing mode. So displacement is nothing but the operand address, whatever may be the address. Then next one, n is equal to 1, I is equal to 0. So now it is indirect addressing mode, and then I is 0. So we call it as indirect addressing mode. Let us see how we will indicate each of these things in the instruction. And next one, n is equal to 1, I is equal to 1. So when both are 1, we make sure it is SICXC architecture. So let's say in a question they give n is equal to 1, I is equal to 1 means we are sure that it is SICXC machine architecture. Then n is equal to 0, I is equal to 0 means it is SIC machine architecture. Then okay, now we had seen all the different combinations of addressing modes. Now we will see different notations for it. Like how do we indicate whether it is indirect or indexed addressing and all such things. So these are some of the notations we have. So first one is indirect addressing. So how do we recognize that it is indirect addressing means you have the instruction and which will be followed by at the rate symbol here, then we will understand that it is indirect addressing. Then immediate addressing. So how do we know that it is immediate addressing? We will have the instruction followed by hash symbol. Then it is immediate addressing. Then format 4. So since we have format 3 and format 4, how do we recognize format 4 is we will have the instruction preceded by plus operator. That means let's say plus add or plus LDA. So it is preceded by plus operator. Then indexed addressing. It is indexed means registers are included. So indexed X. So that is why we will use the register X here. So operand comma X. This is the format or the indication of any indexed addressing. Then character string. Sometimes we will have the character string. Let's say there is one byte or whatever in operand will be there, and then we will have the character C, which is a symbol, followed by any number of letters within single quotes. Then we understand it is character string. This we will see little in detail in the next examples. Then base register, we will use the keyword base here. Okay, and for base register, we are not going to calculate anything else. This is only like a base register active. Then we will see in the object code generation, we will have to calculate the memory address, that is a location of each of the instructions. That's very, very important. We are going to calculate the location, memory location. So how do we calculate the memory location? Let us see in detail. So if the operand field is memory address, let's say add or something, okay, which if at all it is in format 3, then we need to add, that SIC machine takes 3 bytes of memory. Okay, so add 3 bytes to get the next address. Then suppose it is register, let's say add R, register, add addition of the registers. So register format operand, then it will be format 2. Okay, definitely it will be format 2. So as soon as you see register, it will be format 2 presentation. So we will be just adding only 2 bytes to get the next address. Then suppose we have plus operand, plus operator before the operand, then it will be format 4 representation. So we will have to add 4 bytes to get the next address. Okay, of course, yeah, this we will see in the example in detail. Then next one, we have an instruction called RESW. So reserve word, and then there is a space followed by 2000. So what do you mean by reserve word? Let us see. We have to reserve word. How many words? 2000. So reserve word means one word takes 3 bytes of memory in SIC machine, in SIC XE machine. Okay, that you should be known. So one word is equal to 3 bytes. So how many words they have given? 2000 words. So 2000 into 3 bytes, we will get 6000. Okay, and guys, you have to understand that whatever memory address we are calculating, they always should be in hexadecimal. Okay, and even whatever length we are finding out, they are all will be in hexadecimal numbers. So whatever calculations you do, first you are doing it in decimal now as such, then you need to convert it into hexadecimal. Okay, so while calculating the address, now we will come back to this RESW, reserve word 2000. So 2000 is given in decimal. So 2000 into 3 bytes will be 6000, which is in decimal representation. How do you convert it to hexadecimal? You know, decimal to hexadecimal conversion you do. You can use a calculator. And then 6000 decimal equivalent will be 1770 hexadecimal. Okay, so you should not add 6000, you should add 1770 to the next address. Okay, again, you don't have to worry so much. We will see all these in the examples. Same way you have reserve word 1. So just 1. What do you mean by word? 1 byte. Sorry, word means one word will be 3 bytes. So the number 1 into one word will be 3 bytes. So it will be 3. So whether it is 3 decimal or 3 hexadecimal, one and the same. So this value you have to add to the next address. Okay, then we will see how to calculate the memory address for one more type of instruction, RESB, reserve byte. Okay, reserve byte 2000. So in the previous slide, you saw reserve word. Okay, what do you mean by word? One word is equal to 3 bytes. Now this is one instruction, reserve byte. So what do you mean by 1 byte? It is just 1 byte, correct? So the value 2000 constant into byte means 1 byte. So 2000 decimal, that you will have to convert it into hexadecimal. So 2000 decimal is equivalent to 70 hexadecimal. So this you will have to add it to the next address. Suppose I give RESB 4096. Okay, so it is 4096 into 1 byte, which is nothing but 4096 decimal. Equivalent hexadecimal will be 1000, and then this has to be added to the next address. Okay, now again, just before going to object code generation, we have to know few more things. Okay, there are some instructions and directly we can find the object code. Okay, so the first instruction is byte followed by X followed by within single quote F1. So if at all the instruction is byte followed by X, okay, this is very important. We have two things here. One is if at all it is X, then length of the byte will be 1, and we have to add with the previous address, plus its object code also directly we can find out. That is, its object code will be F1. Whatever is the value given within single quote, that itself becomes the object code. Okay, similarly byte x05. So what is the instruction? Byte, so its length will be 1, then x is there, so object code will be 05. Directly it is 05. So this you should be knowing. Okay, then we have next one more type which is known as again byte, but it is followed by C. It is followed by C. So whenever it is followed by C, we will have to check out what is the constant we have here. So the constant what we have is within single quote EOF. That means the letter E followed by letter O followed by letter F. So now how do we find the length of this particular instruction is that now in the previous slide we saw whenever it is byte X it is just one length. Blindly you can go with that. But whenever it is byte C, C stands for constant. Okay, so what is the length? You check out what is the length of this particular constant. How many bytes we have? 1, 2, and 3. So 3 values we have. So the length will be 3. So we have to add it with the next address. And its object code. So how do we find its object code is, check out what is the hexadecimal equivalent of E. I think we will not remember hexadecimal value of all these A, B, C, D or not. Okay, because we are very, we remember the decimal equivalent, ASCII equivalent of E or whatever letters. Okay, so what is the equivalent of E in decimal is ASCII number is 69 in decimal. So when you convert it into hexadecimal, you get it as 45. Okay, so E, the letter E, its equivalent hexadecimal is 45. So add it with the object. Object code will start with 45, then followed by O. So O hexadecimal is 4F. So add 4F and then we have F. F hexadecimal is 46. So you're just adding it. So one by one, all the object, the ASCII in hexadecimal of each of the characters, you're just putting them together. So this is the object code. Okay, now let's see one more. Byte C, again it is C, no? So that means what? It is constant. Okay, it is character and character constant. So what is within single quotes, how many letters we have or how many characters we have? Let us see. Now what is the length? We will see 1. There is one space, right? So that is also taken as one character. So 1, 2, 3, 4. So 4 length will be 4. Okay, and what is its object code? A equivalent, you're writing it as 41. Then space bar will be 20H. Okay, then B will be 42 and then C will be 40. So this is the object code we have for byte C ABs. Okay, so of course we will see all these in detail in the examples later. Okay, now along with that we have to know few more things in finding out the object code. Okay, every time the instructions will not be just format 3 or format 4. We might have even the registers also in the object, in the instruction. So accordingly we will have to take their corresponding ID or the number. Let's say we have some registers A, X, B, S, T, F. These are all the registers which are available in SICXC. So the equivalent IDs are these. I think you can recap this from the SICXC architecture. Okay, so suppose we have some instructions, okay, which are using these registers. Then we will see how to write their object code. Okay, let's say I have an example, clear A. Okay, so this is one instruction. So clear is a register mnemonic. It's a two format registration format. So clear A it is. So what is the register we are using? A. Okay, so the opcode of clear is B4. It will be given in the exam. You don't have to worry and you don't have to remember all the opcodes as such. They will be given in the exam. So clear opcode is B4 followed by what is the ID of A? 0, right? So we will write the ID as 0 here. Okay, so this B4 is opcode of clear. Okay, and then A, this 0 is for register A. Now do you have any other register here? It is just clear A. Sometimes it will be like add R, ADDR, A comma X or S comma A, whatever it. Okay, some two registers will be given. In that time, at that time we will have to take both the registers. But as such now in this particular instruction, we just have only one register. So what is the next register? Do we have any register? No, right? So you will make it as 0. So this is for one register. The next byte will be for one more register. So object code will be clear is B4, A is 0, there is no second register, it will be marked as 0. Okay. Next one, clear X. So clear, what is the opcode of clear? B4. What is X ID 1? Do you have any other register? No. So I will make it as 0. Then clear B. B4. What is B? 3. Then no other register, so 0. Clear S also, same way B4, 4, 0. Okay, now let us see this one. TIXR T. Okay, so this is with indexed value. So TIXR the opcode will be B8. Okay, what is T? 5 followed by any other register? No. Okay, so sometimes you might get something like this also. Okay, it's not that now I have taken mnemonics with only one register. Sometimes what happens is you might get two registers also. Let's say add R, this is one register operation with, let's say, S comma A or something. So whatever may be the opcode of address ADDR, you will write. Okay, then two opcode, the two digits, 2 bytes for address opcode, then followed by S is 4, then A is 0. So this is how it will be. Okay. Anyway, all these we will see in detail. Okay. It will be more clear once we start with the object. Okay.